Performance modeling is a way to analytically capture the performance of an application with more or less rigorous mathematical techniques to figure out what the performance of an application, the overall performance of an application would be. Performance modeling is, as of today, is mostly used by computer scientists. For example, it's used to derive system design. So when you purchase a new system, you actually want the applications on your, to run well on this new system. So in order to do this, you have to figure out what the applications need from the new system. Do they need a strong network? Do they need strong CPUs? Or do they need memory bandwidth or something like this? So those are all parameters that you can combine for your ideal system that runs your set of applications well. What we would like to do, or what we would like to push, is actually use performance modeling during the whole software development cycle. So basically from the very beginning of the application design, which is typically done by application scientists or application experts in their area, they should employ the modeling techniques to choose which algorithms they use, which kernels they implement. Then after they implemented those kernels, they should actually go ahead and check the performance of each of those kernels and compare them to what they should achieve on an actual system. Many people do this, but many people only look at one particular detail, which is the flop count. However, as we all know, that's not very representative unless you're running DGEMM or high-performance LINPACK. So you actually need to look at all the different things that an application performance is composed of. For example, the memory speed, the network speed. Flop counts is one of them. What you do today in order to characterize the performance of an application is you do a measurement series over different input parameters. For example, for the application we're working with, that has an input parameter with a local lattice size. So what you do is you measure different local lattice sizes, then you have a number of points. So the problem with this is, how do I tell somebody about the performance of my application? Well, I can send them 100 data points. The problem with this is too much data. We are advertising some kind of semi-empirical modeling method where we combine analytic methods on the one hand that are strictly rigorous and mathematic, and empirical methods on the other hand, which are based on benchmarks for applications. In order to derive the performance of an overall application, we know that it's consisting out of multiple kernels, application kernels, and each of those application kernels has a specific performance. However, capturing this performance purely analytically is way too complex because computer architectures are way too complex these days, caches are way too complex. So what we do here is we employ an empirical technique to determine the performance baseline of the microkernels, and we then combine them with analytic techniques to the overall application performance. We do the same thing for the communication because we're talking about parallel applications here. So we are determining the communication parameters of the application. We are counting the messages, which is then the analytic part, and then we are combining the measured performance characteristics of the communication, point-to-point microbenchmarks and collective microbenchmarks, together with the message counts into the application model for the parallel model. So what a performance model here does is actually finding a more concise representation of those many data points. So the idea here is that you actually know how your performance is supposed to scale with the application input data. So you create an analytic function, for example, a linear model for the example application that we're dealing with. We're saying the performance is basically linearly dependent on the input parameter volume. And then we only report a single number that gives you the slope of the curve. And this single number can then be used to represent the application performance over all the data points collected. So we can replace all the 100 data points with a single number or with two numbers. Actually, for the application, it's a little bit more complicated than my simple example here. So we have about 5 to 10 parameters. But those 5 to 10 parameters can replace a whole chain of measurements and can be used to communicate those performance model, those achieved performance on a given architecture easily. There are multiple avenues how this can be used. So one of the things is simply to communicate the performance achieved on a given system to somebody else. So for example, if you're writing a publication, you don't have to put all those graphs in there. You can just say, look, this is my performance number A, B, and C. So the second use of performance modeling, which may be more interesting for application developers, is actually to see how well an application is doing on a system. Performance model will actually tell you along different metrics how well you're doing. So as soon as you're maxing out one of those metrics on a given system, for example, if you're reaching the peak flop rate and you can show that your code cannot work with less flops, you can claim that your implementation of this given algorithm is actually optimal on this system. This is a very strong statement. Of course, flop rate may be less relevant for many codes today. For many codes today, we're mostly talking about memory parameters like bandwidth or even memory injection rate, or network parameters, network injection rate. Performance modeling may also be very interesting for operating an HPC data center, because with performance modeling, you basically know what you expect from an application run. So if you had a model for each of the applications being run in the system, you could predict the performance as it should be, and you could observe the performance as it is. And then you could observe potential degradations in performance while you're running your system. So this would be a very helpful technique for the day-to-day operation of a data center too. The second thing we're hoping is getting reasonable feedback from the community what our next steps should be in order to push this performance modeling. So for example, our techniques to apply in practice to real applications, or our techniques to imprecise. Because we're moving right at the boundary, because we have to make those techniques relatively easy. And of course, by making them easier, we're losing precision. Right? That's typical. We're employing easier equations. So our advertised techniques are not as accurate as the techniques used by the computer scientists used before, but they should be just accurate enough to drive action in the application development process. In order to get to exascale, if we ever get to exascale, we need to drive some things to the extreme. Especially parallelism may need to be driven to an absolute extreme. And in order to do this, we need to control the overheads. And performance modeling can give you an estimate of what the overheads at very massive scale will be. And actually, it gives you an estimate today. And that's a good thing. Because today we can't run 1 billion threads anywhere because we don't have such a machine. But we can estimate what the benefit or what the overheads would be at 1 billion threads of our techniques used today, and maybe of the techniques that we may be developing for tomorrow. And so we can actually check how things will behave before we invest all the money and time to develop a code, develop an architecture. And this is one big benefit too. The other benefit would actually be if you're trying to move your code forward to a new computing system, or just to port it to a different architecture, or you want to apply some optimizations. With performance modeling, you can assess the impact of certain changes to your code on this new architecture, or at a different scale, or at a different at a different size of the input system. So without actually performing any coding work or any excessive tests, you can tell how much your investment is going to pay off later.